Thank you.
Okay, thank you very much. So I'm going to talk about some different possible ways to integrate human control in multi-robot systems. And so the second part of my talk will be focusing specifically on autonomous vehicles, although the first part also relates to those kinds of systems. So my lab at Arizona State University focuses broadly on distributed robotic systems. A lot of our work is on developing scalable control strategies for robotic swarms that often have stochastic behaviors and very limited information, such as a lack of GPS or other global position information, local inter-robot communication. We also have some recent work on decentralized control of soft modular robots, which have distributed sensing and actuation. And very recently, we've started to look at integrating human-robot interactions into multi-robot systems and think about the role of the human within what could be a distributed human/robot collective. So there's been a lot of discussion at this workshop on mean field models for traffic. And so we work on mean field models as well as descriptions of robotic swarms. So they have slightly different dynamics that we consider broadly than the traffic systems that we've been discussing. But the concept is the same, that we are abstracting a collective of robots that are moving according to identical controllers. And we're describing the density fields of robots that are at doing different tasks or in different states. We describe the evolution of those density fields of robots over space and time. And so here's an illustration of one possible framework for robots that are just switching from task A to task B at some probability rate. And so you can see that their motion is described by this stochastic differential equation. It has both a velocity field for directed motion, and in this case, it also has a diffusive type behavior to model either programmed randomness, for instance, to increase dispersion so that they can more effectively explore an environment, or modeling noise in the sensing and actuation. So, so given a swarm of robots that are all behaving according to this way, now we can abstract the swarm as a set of advection, diffusion, reaction, partial differential equations. And now at this level, we can use various techniques such as optimal control to design parameters of the robot's controllers to enforce some desired collective behavior that we can often formulate in terms of densities. So at this level, the macroscopic model, we have some kind of human-defined control objective. So depending on the swarm task, a person's going to formulate some optimization or control problem that you can incorporate these equations into, and then the output parameters that you're designing. In this case, it's the velocity field, diffusion coefficient, and probability rates of switching tasks. And this just illustrates here that these rates can depend on space or possibly time. All of these parameters can, in fact. So once you have these parameters, now you have control inputs that you can program onto each robot. And then if you let the swarm go, on average, the swarm will exhibit the desired behavior that you specified at the macroscopic level. Okay, so this is one way to incorporate human input into a distributed robotic system. And it can also be done for mean field models that describe traffic flow to, for instance, reduce density, reduce the traffic congestion along certain roads. So, so this is basically a top-down control approach. And so we can use this approach, so some advantages are that it's scalable with the number of robots, because you're using a model of the collective as a continuum. And so that's independent of the number of robots. Although the variability of the swarm behavior is going to depend around the expected behavior is going to depend on the number of robots. But in any case, the mean field model is amenable to lots of rigorous techniques for analysis and control. And so we have a recent survey paper this is my former student, Karthik Vasuthy, who's at UCLA now as a postdoc / adjunct professor. So we've worked with Andrea Bertozzi on some of these problems as well. So we have a survey about the use of these types of models, specifically in swarm robotics. Okay, so things that we can prove. Here's two main properties that we can ensure about, or that we would want to ensure about our swarm based on the mean field model. And so if we have a human defined objective, for instance, for coverage or task allocation, we want to ensure that the system's going to do what we programmed it to do. So, two important properties are controllability and stabilizability. So this is just a brief summary of what these properties mean. And they're illustrated for an ordinary differential equation system, which doesn't have spatial dynamics. It's just keeping track of the numbers or populations of robots in different states over time. So you have some control system, x dot equals f of xu. So we say the system is controllable if given an initial distribution of robots among different states. For every desired equilibrium, so if we want to drive the system to a certain equilibrium distribution, there exists some control input u such that at some finite time, your system ends up at xd. The property of stabilizability means that if you're given an equilibrium distribution, there is some map k or control input, feedback control law, such that the closed loop system has that equilibrium as an asymptotically stable point. And so there's a lot of challenges associated with these problems, ensuring these properties about mean field models. So some of these are that the control inputs in states have to be non-negative. You can't have negative numbers of robots. There's structural constraints on the control inputs depending on what kind of feedback the robots can get, whether it's local or not. The control problem is nonlinear, and the control system is often infinite dimensional. So just a summary of what my lab has looked at over the past few years. So we've looked at controllability and stabilization of swarms of robots. So to ensure these properties for various types of systems, which are summarized here, they have both spatial and temporal dynamics described by Markov chains, as well as advection diffusion processes, or a combination of both. And so again, you can, if you're interested, you can take a look at that survey paper. Okay, so just to illustrate some applications of the mean field model control approach, include stochastic strategies for spatial coverage or even boundary coverage by robotic swarms. The more abstract problem of task allocation, of which coverage can be viewed as a specific case where the tasks are spatial locations. And you can even look at problems in mapping from a mean field perspective. So I'll just talk about the applications in the upper left in more detail. So this is stochastic redistribution among a set of sites using only local robot measurements. In the middle, this is a leader-based herding strategy, sort of like a sheep herding dog herding a bunch of sheep. So we can also look at mean field models. If we can assume the model of the swarm, we can actually sometimes back out geometric features from just encounter time data with these features. We can also look at other coverage problems where the robots can locally measure something about the scalar field, and their control inputs depend on those measurements, and we can get them to form various patterns at equilibrium. And then we've also looked at designing controllers for robots with discrete time nonlinear dynamics to do similar types of coverage problems. Okay, so this is the first application where we have a swarm of robots. We are modeling them as, or rather also controlling them as switching between states according to a Markov chain. And here, the transition rates are functions of local robot populations. So the robots need to measure the number of other robots in their state, possibly robots at adjacent states. And so we can guarantee that using this feedback in the control law, the robots will converge to the target distribution, and also that they'll stop switching between tasks once they reach that allocation. So again, the control laws are being computed beforehand. So a person somewhere is determining that they want the swarm to rearrange itself in a certain distribution. They might even specify the form of the control laws and then optimize those control laws. So as another example where you might have a person interacting more directly in real time, you can imagine a situation where you have a special leader agent, which could be a person remotely controlling, for instance, a drone that ground robots can sense. And so let's say that it's not really feasible to keep broadcasting sets of control parameters to the robots that you design for various distributions. And so you've sent out the robots, and they all have the same behavior in which if they sense the leader in their state, they will disperse probabilistically to adjacent states. So the leader has this repulsive effect on the followers. And so it turns out that you can actually herd a swarm in this way to a target distribution over space. You can even incorporate inter-robot interactions along with the effect of the leader on the robots. And so here, the robots don't have to have global localization, and the only control parameter here is the leader's trajectory through the state space. So you can guide the leader, the robots will sense it, and then they'll disperse, but they always have the same dispersion probability rate. So you can prove things about controllability under this strategy. You can also prove global asymptotic stability for the case of non-interacting followers if you have leaders with open loop or closed loop strategies. So more details are in this recent paper. And here's a video of both a numerical simulation of 10,000 follower agents that are being herded by this red dot, which is the leader. And here the leader is just going in sort of a lawnmower pattern. It's not designed, it's not optimized in any particular way, although we're currently working on approaches to do that. But you can see that as time goes on at steady state, you get a dense set of robots along the square as is specified in the target distribution. So on the right, this is the same strategy implemented on a remotely accessible test bed, which is called the Robotarium. It's at Georgia Tech. And so you can test your swarm control algorithms by sending your code over to this test bed, and they will implement it on real robots, as you can see. And so we also validated this approach on this test bed where the red dot is representing the leader.
So if I may ask a quick question, it looks like the robots move always one at a time. Is it a choice or a constraint, or is just my impression?
You mean on the
So they don't move together. They seem to move one at a time in the Robotarium and in the previous movie you showed. Or maybe it's my perception, they move all together.
So I think that might have been a part of the implementation, just to enable so that the change in population of robots at different states didn't change too rapidly. In reality, the robots would do this or I guess in implementation, you would want the robots to count their neighbors in a decentralized way. But in these experiments, we sort of simulated that by having an overhead camera and tracking the number of robots in each state. So we had one at a time, but in practice, it should be continuous, that you have robots moving at any time.
Thanks.
Mm-hmm. Okay, so now I'm going to talk more specifically about autonomous vehicles. And so we've seen that for large scale distributed systems, we can abstract the system to a tractable analytical model in the form of a mean field model. And then in the cases I showed, we're specifying the desired behavior at that level and then pushing it down onto the robot controllers. So you can model autonomous vehicles or groups of autonomous vehicles in this way. But there's another factor which we hadn't considered in the previous applications, which is the constraints that arise from human behaviors when driving. So if we are going to deploy autonomous vehicles on the roads, it will be useful to implement human-like control inputs that replicate driver behaviors. And so why would we want to do this? So crashes and accidents with autonomous vehicles are inevitable. We've seen many of them in various, accidents that have happened recently. But so the AVs are moving around in these uncertain dynamic environments. And so they often might need to make decisions very quickly in unanticipated situations like imminent crashes. And the human may not be paying attention. Maybe it's a level 4 or 5 AV, or maybe it's level 2 or 3, but the person is just trusting the vehicle to make the decision and can't react in time. So I've been working with Ted Pavlik, who's here, and Kathy Johnson, who's a psychology professor at ASU. And we've been thinking about the idea of designing AV behaviors to align with those of trustworthy human drivers. So drivers who don't have many traffic citations and that have positive driving behaviors according to some metrics. And so we propose that if we design AV controllers to mimic various human driving styles, that could be beneficial in different scenarios. So maybe you want to mimic an ambulance driver versus a school bus in different scenarios. And also if the AV is behaving as a trustworthy driver, then this can also enhance appropriate trust by the public and hopefully increase acceptance of autonomous vehicles if they are behaving like moral agents, even if they actually aren't. So in order to do this, we would need to obtain data on human driving behaviors. But because we're focusing specifically on risky scenarios, like imminent crashes, we want to do this in a safe way that doesn't involve full-scale vehicles and potential damage like that. So our approach here is to look at 2 different platforms. One is a driving simulator. And this has the advantage that you can construct a lot of different traffic scenarios in a simulator. And they've gotten very realistic. We're also developing a small scale physical test bed to actually convey to the human driver who's remotely controlling or remotely driving a car, we want to convey a sense of the actual cost of physically damaging the vehicle or the surrounding testbed environment. So with a driving simulator, you may not have a sense of that cost because you can run into things in the car, nothing's going to happen, nothing's damaged. So in addition, both of these platforms, we think, can elicit the real-time psychological and neurophysiological responses that actually influence driving behaviors. And so this provides an advantage over another tool that's been widely used, which are surveys, such as the Marl machine work that was done. And so the surveys, of course, can allow you to sample a huge amount of data from lots of participants across the world, which is what they did in the Marl machine experiment. However, it doesn't have this real-time aspect where a person would be driving in real time and has to make a split-second decision, because you can actually deliberate on what your solution is to the trolley problem when you're looking at a picture of it. So I'm going to discuss these platforms that we've been developing. And so this work, a lot of this was done by master's students in my group over the past couple of years. So on the left, you can see this driving simulator station with this curved monitor. And so we use the simulator platform Carla, Car Learning to Act. And so what we did as preliminary tests, we simulated a variety of trolley problem-like scenarios where a person is driving using this Logitech steering wheel and pedals, and then they're confronted suddenly with this unavoidable crash, and they have to steer in one direction or another. So we've been taking some preliminary data on this. And so my students have improved this station and the simulator. So now this is an example of 3 different trolley problem scenarios that are simulated on a course. And so this is just some sample data. You can get the trajectory of the vehicle as the person's driving it. You can get the corresponding sensor data from the car. You can see where they collide with things and what they crash into. So you can obtain a whole host of human driving data on many different scenarios. And moreover, you can connect their responses to pre or post survey data that evaluate various driving characteristics that you can even relate to things like their values profile or moral priorities. So this is, we're thinking of as one platform for obtaining driving data that can be translated into autonomous vehicle control inputs. And another platform is this small-scale driving testbed, which involves a miniature robotic car, which we call Gochart. And the name chart comes from the center of which I'm an associate director. And it stands for the Center for Human Artificial Intelligence and Robot Teaming. And it's part of the ASU Global Security Initiative. So that's why this word chart keeps appearing. Okay, so we developed a miniature robot called the Gochart, and this emulates an autonomous vehicle. So it's a 1/28 scale model of a commercial sedan, and I'll go over its various capabilities. So we want to use it in, sorry, it's going forward. All right. So we're building testbed environments in which the robots can either drive autonomously or be remotely driven at a driving station, similar to what you saw with the simulator station. And so we want to be able to reproduce conditions and challenges that are similar to what an AV would experience in reality. So another motivation for developing the testbed is to test various deep learning techniques, computer vision algorithms, and controllers. And also to study interactions between human-driven vehicles and autonomous vehicles, things that are too risky to test at full scale. So here's a view of our miniature testbed environment. So you can see it has traffic lights, traffic signs, roads, intersections. And now here is an image of the Gochart Robot on the left. So it's a fairly small platform. It's less than $300 cost of parts. It does have an external GPU, which is a few $100s. So you need to add that into the cost. But the platform itself is fairly inexpensive. So the Gochart has a variety of sensors that are similar to what you would find on a full-scale car. It has a 2D LiDAR on the top, and it also has 4 cameras, so 2 on the side view, 1 in the rear view, and an ultra-wide night vision camera on the front, as well as an ultrasonic sensor. And it has an accelerometer and can measure its heading and heading rate change as well. Okay, so here's the control architecture. And again, the robot has both an autonomous mode and a remote control driving mode. So there's a Jetson TX2 in order to process large amounts of data, like vision data for doing tasks like object identification using deep learning algorithms. It has a Raspberry Pi 3, which does the high-level control tasks and runs the robot operating system. And there's a Teensy microcontroller for the low-level tasks like getting sensor data and driving the motors. Sorry. So here's what the driving station setup looks like. And so you see there's a GUI here with views from all 4 cameras. So all 4 cameras are streaming video that the remote driver can view. And they can also steer and use the pedals. So this video is showing that. So on the left, he's steering and viewing the first person view through the robot. And on the left, on the right, we see the robot going, so it can detect, well, that's autonomous mode, but in remote control driving, it can detect a red light and stop, as we'll see. So here's some autonomous lane tracking algorithm that was implemented. So now the robot's driving by itself. You can see its front view camera on the left. And so here it's using the OpenCV library to detect the lanes and track them. Here's an approach using autonomous object detection using the YOLO v3 technique. So this is using deep learning to classify objects with some percent confidence. So here it can detect traffic lights, whether they're red or green. It can also detect other object classes like stop signs. And I'm gonna just go back for a minute. So now this is an example where it's classifying another Gochart. And so it stops here at the intersection. It waits for the car with the right of way to go forward. And then it continues on its way. Okay, so sorry about that. All right, so we've been working on developing another larger test bed, although it's still a small scale test bed. So this is what we call Chartopolis. It's being done in collaboration with other faculty at ASU. And so this test bed has reconfigurable buildings. It will include adjustable lighting, traffic signs, media projections to customize the environment. Right now you can see it, so it can cast shadows, and we could do all sorts of testing for autonomous navigation in low, for instance, low lighting environments. And in addition, we're modeling the test bed in the Carla simulator on the right so that we can have a common environment to test in both simulation and in the physical test bed. Okay. So that's actually all I have. And I know I'm kind of early here, but this is my lab. And so they've done a lot of this work, and we are supported by the agencies at the bottom. So thank you. And I'm happy to talk more about any of these aspects.